Let me start the first part of the lecture, which where we will talk about the singular point of an analytic function. First, what we mean by a singular point, and a straightforward definition, a very wide and broad definition can be like this: a point z naught is a singular point. A point z naught is a singular point or a singularity, whatever, of analytic function f z if f is not analytic at z naught. I mean, a singularity is something, a point is singular. Singular literally meaning it is an individual point, a very special, unusual point. And of course, it is unusual if we are talking in terms of analytic function. So function is analytic, not analytic at that term, but it does not make it a singular kind of thing, literally meaning. So we will write a restrictive definition. So that restrictive definition will be covering all the functions we are familiar with. And nothing very great about the restrictive definition. It says simply that I will say a function is singular, has a singularity at point z naught if fz is not analytic at z naught, but fz is analytic at some point, maybe more point, but at some point of every neighborhood. Neighborhood, here I take neighborhood, you can take a disk or you can take open set of the point z naught. So roughly speaking, my function, there will be an open set u, and this is the point where function is not analytic, and whatever neighborhood I will take, I'm saying at some point, these points may be more, at least one point, every neighborhood will contain where function is analytic. So this definition throws, of course, the possibility of isolated as well as non-isolated points. So I will concentrate the classification, the nice classification of singularity occurs when you talk about the isolated singularity. But of course, there are non-isolated singularities also as well. For example, log z is a multi-valued, you say multi-valued function. So to make it single valued, or more than that, to make it analytic in maximum part of the plane, you make a branch cut. Branch cut is an idea. So, for example, just giving you the idea. So branch cut is something like this. So here I have written the example I have given of a log function. It is a principal branch, it is called. Here I have made the cut. Here I have made the cut along the slit. I have taken a cut. This part this is called branch cut, and so z is not 0 and all negative real axis. So this has been removed, and now and this is called, this cut is called, you have made the cut at theta equal to pi. So this is a branch cut, and it is a starting point of this cut. Then this function, this is called principal branch. When this cut is like this, function is analytic everywhere. So you can make, you can make any cut like this. You make this cut here, theta equal to some alpha, and starting from origin, you make this cut, and then you can define your log function. It will not be called principal branch, but it's a branch. It will again make your log function single valued and analytic in whole part, in other part. And the common point of these branch cuts is called branch point. And you see, branch point is very interesting point. Although all points of the branch cut, all points of the slit will be singular point by your definition. And especially this branch cut, which is branch point or any other point. This is one of the example of non-isolated singular point, because in any neighborhood of this branch point, you get point where function is analytic, you get point where function is non-analytic. So multi-valued functions with branch cut, if you consider the branch, then the branch point will be a non-isolated singularity. So this is the example. And if you want some easier example, then see here. This example you take fz equal to sine 1 upon z. In this example, you will find that z equal to 0 is non-isolated singular point, because all other not one up, sorry, 1 upon sine 1 upon z. So all other points are 1 upon n pi, where n belongs to non-zero integer. These are all isolated singular point. But 0, because their limit point is 0, so 0 is not an isolated singular point. So now we come to the definition of isolated singular point, which is more important for us. So if U is any punctured neighborhood, punctured at a point z0, so that function from this punctured neighborhood to complex plane C is analytic, then z0 is called isolated. Means this is the point, every point function is in every place. This yellow shaped all point function is analytic, but at z0 function is non-analytic. So this is a isolated singularity. For example, take 1 upon z, and this function has only one singular point, that is z equal to 0. At every other point, this function is analytic. So z equal to 0 is the only isolated point. Now, we will do the classification of isolated singular point. A very final classification is available for isolated singular point. What classification is available? Classification is available like this. So if isolated singular point can have three kinds. One is called a removable isolated singularity. Second is called pole, and third is called essential isolated singularity. So these are the three kinds are possible for isolated singularity of a function which is not analytic at z0, but analytic in a neighborhood in an open set around that every point of the open set around that. So first is, for example, see sin z equal to sin z upon. Why it is this removable singularity also called the false singularity? In the sense, because take the function f z equal to sin z upon z, and you will note that this function is z equal to 0 is somehow this function is not defined at z equal to 0. Z equal to 0 is a singularity, and it is an isolated singularity. But the limit of this function exists at z equal to 0. That is 1. So if I define a new function gz, which is sin z upon z when z is not 0 and 1 when z equal to 0, then you can say this gz, this new function is analytic at z equal to 0. It will be an analytic function at z equal to 0. So if it is an analytic function at z equal to 0, so it means what can I do? So this value I have given. This function becomes analytic. So gz is equal to fz. Gz is analytic. Why? Gz is analytic by this very beautiful theorem. That is the application of Morera's theorem. Which says that if f is continuous at continuous, if f is continuous in an open set D and f is analytic everywhere except at points of line segment L line, then f can be to be x. So x can be extended to x, then f, then f point except at points except at points of line segment L, then f is analytic D, because f is already defined in D. So it becomes very easy for me to define. So gz is a holomorphic function in whole of neighborhood of 0. And it is a holomorphic function which is equal to fz. Fz not equal to 0. So fz can be given this value actually. So, and actually this theorem is very beautiful application of Morera's theorem, this theorem which I have just quoted. So anyway, so here we come to another part, which is a Riemann extension theorem, and it is a very special case. This theorem says, I say here, I will write here, that is called Riemann removal singularity theorem. What it says, Riemann removable singularity theorem says that if function has f is analytic in a punctured neighborhood at z0 and limit z goes to z0 fz, limit z goes to z0 z minus z0 fz is 0, then f can be extended to an analytic function to whole of the neighborhood. So this is the Riemann, very famous Riemann, actually in a unique way. It can be extended in a unique way. This is the defining property, which I think I have written somewhere also. This defining property I have written somewhere. This is the removable singularity. This is if and only if case. And actually, Riemann extension theorem, this it's a special cases here. I am writing special cases. If f has isolated singularity at z naught and f is bounded near z naught means in some neighborhood of z naught, then z naught is a removable singularity. Singular singularity means uh, you can define function across z. You can redefine or define the function f so that singularity is removed. And sometimes, therefore, it is a region. Sometimes this singularity is also called false singularity. So anyway, for example, I demonstrated fz equal to ez minus 1 upon z. So z equal to 0 is isolated singularity. And limit z goes to 0, z minus 0 e to the power z upon z is 0. So conforming to this property, if and only if, it means z equal to 0 is singularity, removable singularity. Now the second singularity is very interesting. In the first and second, there is a very nice relation between them. In this case, second singularity is a singularity. An isolated singularity is pole. It's a very simple thing. So in some neighborhood of that point, a function will blow up. So this is a pole. Then if you take the value of function there, function will blow up. Function will blow up. Blow up means in some way. And what is the way? That limit z goes to z naught fz, the limit of function when z goes to z naught becomes infinity. See here, when I say limit, when I use limit, then in this sense I am saying this thing: limit z goes to z naught mod of fz becomes infinity. And in fact, z goes to z naught also has the measurement like this. Z goes to z naught means z minus z naught mod goes to 0. So fz goes to infinity. So this why I'm saying mod, because every the limit is only meaningful with respect to a metric in general. So here, if your complex plane is already a metric space with the usual metric, which is Euclidean metric. So, but we will not mention all the time mod. But you must understand that whenever I am talking about the limit, I'm taking that limit in the sense of modulus. So anyway, this is not a main point here. So, what is the defining property of? So that's a very interesting thing is here. Actually, a function uh, is analytic. It is a pole of order m. We say if function can be written, if and only if that function can be written in this form: gz upon z minus z naught to the power m, where gz naught is not 0. It is not 0 at z naught is not a 0 of gz, and gz is analytic at z naught. So it's a very nice defining property. And actually, this property is if m equal to 1, this is called. So this property is something you can understand by this thing. So it is coming. It's a very nice property of pole. So see, numerator. You are maintaining numerator or something, and denominator actually becomes 0 at some point. So something non-zero divided by 0, to blow up case comes here. So what is so I simply illustrated by this thing. For example, if I give you a rational function Rz Pz upon Qz, so rational function, Pz and Qz are polynomial. Pz and Qz are polynomial, and naturally qz, the zeros, the, the zeros of qz will for the singular point, if there are singular points. So, for example, if pz is not 0, suppose pz is not 0, or z naught is not 0, and this qz naught is 0. So I will say, I think it is better if I say this thing. But I say, uh, it is better if I say in this term. So suppose qz. So I just want to say this term. It is easy for you to understand. I say this. Suppose qz is written as z minus z naught. So it is simply like this, qz, where q z naught is not 0. And pz naught is also not 0. So in fact, qz you can make it's a 0 free. So so all the zeros I have taken. So all zeros you can take. Suppose. So this rz is something like this. And qz z naught is not 0. And I say, in fact, I say qz is not equal to 0. So it is better if I say qz is not equal to 0. Then pz is not equal to 0, qz is not equal to 0, then this is very much analytic function, and this rz, this function, will have pole, z naught will be pole of this function. It can be removable singularity also. Suppose I write, I take at z naught, suppose z naught, I make it z naught, this pz, I take, if z naught is a 0 of type this n, and now this pz, where pz naught is not 0, because zeros will be discrete, and here z minus z naught m qz, and qz naught is not equal to 0. It means pz upon qz analytic at z naught, and the neighborhood of z naught. Both are pz upon qz is not 0 actually. So it is analytic in some neighborhood of this thing. And now if n is greater than m, then you know that z naught will become a removable singularity. If n is less than m, then z naught will be a pole. So in case of rational function, there is only two kinds of isolated singularity. Either it will be removable, or it will be a pole. So here I should say qz naught not equal to 0. So in the neighborhood of z naught, we can find this thing. So anyway, so you can just do the calculation, and you can make the things. So this is about pole. So if fz has a pole of order m at the point z naught, then Fz can always be expressed in the form Gz upon Z minus Z naught to the power n, where Gz is not zero at Z naught and it is analytic at Z naught. And if m is equal to 1, then we say it is a pole of, it is simple pole of order 1, and it's called simple pole. So sine Z upon Z square, where Z equal to 0 is again a pole, and this is a pole of order 1. But here is, I give you another characterizing property of pole. A point Z naught is called pole of order m if and only if this condition, this very nice condition, if it happens. And it seems very natural. See, Fz multiplied by Z minus Z naught to the power n, and you take the limit comes out non-zero, and if it multiplied by Z minus Z naught to the power n plus 1, it comes out 0. Then Z naught is called pole of order m. And see, you can demonstrate for this function here. I have demonstrated for this function. So it is a pole of order 1 sine Z upon Z square. Fz is sine Z upon Z square. Here I have written multiplied by Z, and if I take limit, it will be 1, not 0. If I multiply by Z square, 1 plus 1, and take the limit, it is 0. So it is a pole of order 1, a simple. It is isolated singularity, which is not a pole, not a removable singularity, both are missing, then that singularity is called essential singularity. And essential singularity is something you will say that see, essential singularity is, it is neither pole nor removable singularity. Means in the neighborhood of that singularity, functions not blowing up, and it is not actually taking any kind of limit also. For example, e to the power 1 upon zc. Z equal to 0 is a isolated singularity. And if if Z moves to 0 along positive real axis, that goes to infinity. If it moves along 0 along negative real axis, it goes to 0. So with two different paths, you are getting two different limits actually, and that itself says that it can never be a pole because it is not blowing when Z goes to something, and it can never be removable singularity. So what is left? Simple thing is, it is isolated singularity. And then see, some people will say, after seeing all these things, all these three classifications, you will say, see, pole is very bad because something blow up. In essential singularity, okay, it is, sometimes it looks if different path you follow. Or for example, you take this function. Suppose you take this function, fz equal to sine 1 minus 1 upon z. So you can check here very clearly, z equal to 0 is isolated singularity, and if you move along positive real axis, so it goes to 0 plus, z goes to 0 plus, then you see that limit oscillate between plus minus 1. So it is essential singularity. So oscillation is there. So in some sense you will see, so I can roughly say that if at a singular point function is not blowing up, it is some kind of bounded behavior is there, then it will always give you the chance of making it analytic across that point, and singularity will be removed. If it is blowing up in that sense that if we near at a point, if I take z near to that point, that isolated point, and function's values, its modulus values goes to infinity, it means it's blow up. It is simply a pole. And if never such this type of nothing like this happens, nothing like first or second happens, then we say singularity is essential singularity. And there is a some people will say that pole is a bad kind of thing. No, this is not the case. Actually, if it depends how you see the things. So there comes the concept of meromorphic functions. So poles are the only discrete points where the functions is not taking anything. So these functions are called, if poles are the only discrete point, and then function is called meromorphic functions or meromorphic functions or meromorphic. It is called meromorphic functions. And actually, you can if you that the isolated points are poles are there, and you go from here to extended complex plane, that is called Riemann sphere. So it makes generally it gives a very nice idea of holomorphic function. You can again you can retain holomorphic function. What you do if pole singularities are only poles, then what you do, those poles will, you do one thing. Poles are mapped to infinity. Then this function, this Riemann sphere, this function is called then f is called C kept holomorphic. Means you are going from C to, so it is your perspective you have changed of seeing the function. So anyway, there is another important thing, and what I want to say that essential singularity is bad actually. Instead, the essential singularity is bad. It is Casorati-Weierstrass theorem. Casorati-Weierstrass theorem is there, which says if you take any neighborhood of Z naught, and you take the image of that neighborhood under F, and you take its closure, it becomes whole complex plane. Means you choose any neighborhood of essential singularity, every point of that neighborhood can be its value under F can be made arbitrary close to a complex number, to any complex number. So this is a Weierstrass Casorati Weierstrass theorem. So this type of phenomena happens with the essential singularity. So we finish this part here. I have assigned you, you will get a set of uh, multiple choice questions, which you can try. You can apply whatever I have said here. And the next part, we will do a singularity with the help of Lorentz series. And there, the things will become, calculation will become much easier, I think. Here the derivative and all these things are involved, the calculation will become much easier. So here I finish the